This video will describe the two most popular graphs of quantitative data and then go on to describe the summary measures that are typically used to describe the center and the variability of the data. The graphs will be histograms and box whiskers plots. To describe the center, there are three popular measures: the mode, which is the least reliable, and what it does is it counts the most frequently occurring data. It's the least reliable because it varies from sample to sample. The median is more reliable. It is the data value that's in the middle. It's the 50th percentile. It's a single number. The mean is the most reliable and more difficult and time-consuming to calculate. It is the average of all the data values. Equally important as where is the center of the data is how spread out the data is. What is the variability in the data? The range is the least reliable measure of variation. It is quite simply the maximum value minus the minimum value. The interquartile range is more interesting. What it does is it takes the difference of the 75th percentile, which we're going to call Q3, and the 25th percentile, which we're going to call Q1. The standard deviation is the most reliable. However, it takes every data value into consideration, and it measures how far is that data value from the sample mean. I think the interquartile range deserves a little more attention. Here's a picture. Here's Q1, the first or lower quartile. It chops off the bottom 25%. It is the 25th percentile. Then right in the middle is the median. The median is the 50th percentile. Half of the data is below the median, half of the data is above the median. It's also called the second quartile. Over here, we have Q3, or the third quartile, or the upper quartile. It is the 75th percentile. Below Q3 is 75% of the data, and above Q3 is 25% of the data. So what the quartiles do, Q1, Q2, and Q3, they break the data into four parts, equal parts, percentage-wise. The lower 25, the middle 25, and the upper 25. The interquartile range talks about the middle of the data, the middle 50%. It is Q3 minus Q1. So interpretation, it is the variability of the middle 50% of the data. The standard deviation. I'm sorry to have to show this to you. The computation is very difficult to do by hand. You would definitely need either a statistical calculator or, better still, a piece of good computer software. The one we're going to use is StatCrunch. What does the standard deviation do? It talks about deviations from the sample mean. How far is the data value from the sample mean? And then we square them because we don't want positive and negative values to cancel each other out. And then we add all those deviations from the mean up. And then we average them, so to speak. It's a sample value, hence it's divided by n minus 1. If it was the real thing, the real standard deviation, the population one, it would be dividing by n. But that being said, the units will be wrong. The units here might be milligrams squared. To get it back to the original units, we take the square root. Nobody nowadays does that by hand. But we want a picture. We want a picture that shows us what a small and a large standard deviation means. Sigma is the symbol for the population standard deviation. Mu is the symbol for the population mean. So, if the standard deviation is large, that means the data is far away from the mean. Things are spread out. The graph is kind of flat, a lot of variability. If the standard deviation is small, things are tightly clustered. The data is much closer to the mean. The graph is less spread out. Okay, let's move on to graphs. We've talked about measures of center, measures of variability. Let's talk a little bit about how we graph the data. Perhaps the most common and well-known graph of numerical data is the histogram. What you do is you order your data from smallest to largest, and you realize your data spans from, these are daily temperatures, from 10 degrees to 60 degrees. And then you make a judgment about how you're going to divide up the data into different or equal frequency classes. All right, so the first class in all of these classes have a length of 10. The thing is, 20 occurs as the boundary on the first and the second class. What are we going to do? There's a convention. If a number is on the boundary, we put it into the subsequent class. So this 20 would go in here. You'll notice one of the things about the histogram is there's no gaps. What does the height of each of these bars represent? It represents the frequency. The first class interval had a frequency of 3. The second class interval had a frequency of 6. It's very simple, very easy to understand. The modal class, the one that occurs most often, is the class that goes from 20 to 30. Now, we don't refer to the mode as an interval. We're going to look at the midpoint. We're going to say this histogram is telling me that the mode is approximately 25 degrees. We'll talk a little bit more about shape, a little bit, later on. I'll give you a preview. This doesn't look symmetrical to me. There seems to be more data on the right-hand side than on the left-hand side, but we'll talk about symmetry later. We already talked about the interquartile range when we talked about variability. It's the third quartile minus the first quartile, and what it measures is the middle 50% of the data. It's the width of the box, variability of the middle 50%. What are some of the negative aspects of the IQR? It has blinders. It can't look outside of its box. It can't look at the bottom 25%. It doesn't look at the top 25%. As a result, it is not sensitive to outliers. If there's some really large values, the IQR does not detect it. Or some really small values, the IQR does not recognize it. We're going to pass on that and come back to it. Okay, so here's the official picture of a box whisker plot. So we have one way of displaying the numerical data. Here's the other one that might not be that common. Here we have our box. Here we have the quartiles forming the hinges, the lower hinge, the upper hinge, and the median forms the middle hinge. Median is not necessarily, is called an outlier, a high outlier. And how do we depict it on our graph? By little asterisks representing how far it is from this whisker, which represents the largest number that's not an outlier. So this data set has 1, 2, 3, 4 outliers. The further away the outlier is, the bigger the outlier is. On the lower end, the lower fence, you take Q1 and do a similar thing. Subtract 1.5 times the width of the box. Use your fences to decide on any outliers. All values that fall outside your fences, they are outliers. Okay, I think I'm going to end here. It does go on. No, maybe not. We can do it here. Skewness. What is skewness? Okay, well, let's look at it before we make some decision. Here's some pictures. This is symmetrical. The right-hand side looks like the left-hand side. If it's symmetrical, it means like if you put a vertical line through the center here at 3, you could fold it and the right-hand side would completely overlap the left-hand side. And in those cases, the mean and median are the same. So it doesn't matter which one you quote. You could quote the mean, and that would be a good representation. You could quote the median, and that would be a good representation. But maybe not if it's skewed. Two kinds of skewness. Skew to the right. The tail goes off to the right. More of the data is on the right-hand side. More of the boxes are on the right-hand side. That's what it looks like in a histogram. What's going to happen? The mean is going to be over here because it's going to be influenced by these larger values. And the median is going to be over here because it's interested in cutting the data 50-50 in terms of area. So this is important. If it is skewed to the right, it does matter. The mean will be bigger than the median. So if you have a data set that is skewed to the right, you're going to prefer the median because the mean is going to be misleading. If it's skewed to the left, and a lot of the data is on the left-hand side, the mean will be bigger than the median. That's called a left skew or a negative skew. And the mean, again, will be misleading because it's influenced by all of these small values. Can you see skewness in a box plot? Yes, you can. A symmetrical box plot, the bar will be right in the middle. The median will be right in the middle. A positive or right skewed, the bar will be over here. A lot of the data will be on this side. It cuts it 50-50, but a lot of the data is over here. Negative skew. A lot of the data is going to be on the left-hand side. Still, I mean, there'll be 50% in the middle, but the median will be over here. So what are some good things about histograms? You can see if it's got one or two modes. It gives you a better idea of the shape of the data. Box whiskers plots give you a more concise summary, that 5-number summary. They're easier to draw, and this is really important. They show outliers. On the downside, they do not show you the mean or the mode or the standard deviation. So what have we learned? Especially from this picture, if the distribution is skewed, you prefer the mean. In fact, you prefer the mean and the standard deviation, because what's going to happen? The standard deviation is going to be, if you look back at the picture, and this is one reason I shared the formula with you, the standard deviation takes into account every data value. And if it's skewed, there's going to be a lot of either big values that are going to make the standard deviation bigger, or there's going to be a lot of small values that's going to make the standard deviation bigger. So if it is skewed, what do you want? If it is skewed, you want the median and the IQR. The median and the IQR. Okay? All right. Well, I probably overwhelmed you. I'll try to break this into a couple of parts and have a separate little video on each. But that's the big summary of numerical data.